Deep in the Himalayas, where cliffs fall straight into a narrow gorge and wind tears through the valley below, engineers made a decision that should never have worked. They chose to run a full-speed railway 359 meters above a raging river in a region shaped by earthquakes, landslides, and extreme weather. Suspended above this void now stands a single steel arch, rising higher than the Eiffel Tower itself. At the height of a 90-story skyscraper, it spans empty space where mistakes do not mean repairs. This is the Chenab Rail Bridge, the tallest railway bridge ever built. Please take a moment to subscribe and like the video. It really helps the channel. The bridge sits in India's Jammu and Kashmir region, in the remote Riyasi district of the Himalayas. On a map, it looks isolated, but its location carries huge importance. For decades, Kashmir has been shaped by its geography. Each winter, heavy snowfall and frequent landslides block mountain roads, cutting off access for days or even weeks at a time. Supplies slow down, travel becomes dangerous, and entire communities are left isolated. The Chenab Bridge exists to change that reality. It is a central part of the Udhampur to Srinagar to Baramulla Rail Link, a 272-kilometer railway designed to provide year-round rail access to Kashmir for the first time in history. Building this line meant crossing some of the youngest and most unstable mountains on Earth, requiring 943 bridges and 36 tunnels. Among all of them, the Chenab Bridge is the most demanding section of the entire route. If this bridge failed, the railway would fail with it. The numbers behind the Chenab Bridge explain why it stands apart from anything built before it. At 359 meters, it is taller than every railway bridge on Earth. Its total length stretches 1,315 meters across the gorge, while a single steel arch span of 467 meters carries the majority of the load. More than 28,000 tons of structural steel were used, each piece fabricated with extreme precision. The bridge is designed to carry fully loaded freight and passenger trains, weighing over 4,000 tons, moving at speeds of up to 100 kilometers per hour. Even under these conditions, movement and deflection remain tightly controlled. Engineers designed the structure to remain in service for at least 120 years, accounting for corrosion, fatigue, earthquakes, and extreme temperature changes. This is not just a record-breaking bridge. It is one of the most extreme infrastructure projects completed anywhere in the modern world. The greatest challenge was not height or distance. It was nature itself. Temperatures here drop to minus 20 degrees Celsius in winter and rise to more than 50 degrees Celsius in summer. The narrow gorge forces wind to accelerate as it passes through, creating gusts that can reach 266 kilometers per hour. Even while trains are operating, the bridge is certified to function safely in wind speeds of up to 100 kilometers per hour, with real-time monitoring systems ready to restrict traffic if conditions worsen. The region also sits in Seismic Zone 5, India's highest earthquake risk category, with the potential for earthquakes exceeding magnitude 8. Before any steel could be lifted into place, engineers faced another problem. There was no access to the site. Roads did not exist. Equipment was carried by foot, transported across the river by boat, and hauled along temporary paths carved into near-vertical mountain slopes. Before the bridge could be built, engineers first had to reach it. At this height, traditional bridge designs were never an option. The Himalayan rock around the gorge is fractured and unstable, making tall towers risky and impractical. Forcing massive vertical loads into weak ground would only invite failure. Instead, engineers chose an arch. An arch transfers forces sideways into the mountains on both sides, locking the structure into solid rock and growing stronger under load. At Chenab, this design eliminated the need for deep foundations in unstable terrain. Years of wind tunnel testing and computer simulations refined the arch's shape, ensuring it could handle earthquakes, extreme winds, temperature shifts, and moving trains. The arch was not a design preference. It was the only solution that could work here. Construction meant working without ground support hundreds of meters above the river below. There was no scaffolding reaching the valley floor. Instead, engineers stretched a cable crane system across the gorge, anchoring it deep into the mountains on both sides. From this aerial network, steel segments weighing tens of tons were lifted and positioned with exact precision. Construction moved forward from both sides at once, with temporary cables holding each new section in place as the arch slowly extended over empty space. Every connection became permanent the moment it was installed. There was no room for correction. In April 2021, the two halves finally met at the center of the gorge. The final piece, known as the golden joint, locked the structure together. For the first time, the bridge stood on its own. Once completed, forces continued to act on the structure. Sunlight does not heat the bridge evenly. One side may expand while the other remains cool, creating visible movement across the span. Over a structure this large, even small temperature differences matter. To manage this, engineers designed sliding bearings and expansion systems that allow controlled movement without damaging the track or steel. The rails are pre-stressed to maintain alignment as the bridge expands and contracts through the seasons. The bridge does not resist movement. It absorbs it and controls it. Even the sun had to be engineered for. The Chenab Bridge is also a strategic structure. Located roughly 63 kilometers from the line of control, it was built to military-grade standards. The steel is blast-resistant, and key structural systems are duplicated, so the bridge can continue operating even after localized damage. A multi-layer corrosion protection system shields the steel from moisture and temperature extremes, with major maintenance planned at 15-year intervals. Every design decision prioritized resilience, reliability, and long-term operation. This bridge was not built simply to last. It was built to survive. The Chenab Rail Bridge was approved in the early 2000s. What followed were nearly 20 years of geological surveys, design changes, technical breakthroughs, weather delays, and construction challenges. By 2024, trial runs began with sensors tracking vibration, wind behavior, load response, and thermal movement. By 2025, the bridge entered its final integration phase as part of the larger US-BRL corridor. 2 decades after it was first imagined, the impossible stood complete. As trains begin moving across the Chenab Bridge, its real significance becomes clear. This structure is not just about records. It is about access, reliability, and connection. It delivers an all-weather rail link to a region long constrained by geography, strengthening economic ties and reducing isolation. More than that, it marks a shift in what modern engineering is willing to attempt. In one of the harshest construction environments on Earth, a bridge once considered impossible now stands complete. This is how the modern world is built. This is Unthinkable Build, bringing you the stories behind the world's biggest projects. Subscribe for more.